Okay, the last thingy with partial fractions. And this one is, what if you actually have factors that are greater than linear, if they're second or third degree? I'm going to show you a couple examples and we'll just solve one of them. You're not going to see that many of these problems, so I just want you to get the idea. So you can see here that if I factor the denominator, and it just so happens one of the factors is a quadratic, or even, oh my, a cubic. In those situations, that's where we're going to use this whole idea of the quadratic factors. So here's what we're going to do. The exact same thing you did before. Write out the correct number of factors for what's shown. Now when we do this, of course, you write out one fraction for each factor that you have. If we had 3 factors, we'd have 3 fractions. If we had 4 factors over here, we'd have 4 fractions. We're keeping it a little simpler. But you'll notice also for the repeated version, just like in our last video, if you have the exact same factor squared or cubed or whatever, I'm writing out 2 fractions here, 1 to the first power, 1 to the second power. Now here's where it gets trickier or different. Is it really harder? It's harder to solve. You see how this is a linear equation. This is to the first degree. So we're just going to write something to the 0 degree. A times x to the 0. This is a quadratic. So we are going to write 1 power less. We're going to write a linear equation up there. If you have a quadratic, make sure you make it a linear equation on top. It might cause you to have a lot more variables to solve for. It even gets more complicated when you have a cubic, because if you had a cubic, you have a lot more letters there. Now this can get really, really complicated fast. We're not going to do problems that are quite that hard, but they are going to sometimes involve quadratic factors, and maybe even repeated quadratic factors. Let's use that middle one as an example. So we're going to go ahead and multiply through by that common denominator. We'll see what we get. Much of this is going to divide out in that situation. Term on the left, everything divides out. The next term over, oh well, not so lucky, but some of it divides out. And then finally the last one, we've got that there. Now this gets a right bit messy here, and you can try and pick out what you want to plug in. Maybe it'd be good to go ahead and FOIL what we have on the right-hand side. And that looks absolutely miserable. But what I'm going to try and do is organize this a little bit. I'm going to put all the x cubes together, all the x squareds together, all the x's, and then all the numbers. So I'm kind of hyper-organizing here. You'll notice anything that had an x cubed goes here, x squared, x, and then just my plain old numbers. Now the good news is that we can figure out what some of these numbers are really quickly. It turns out that on the left-hand side, we don't have any x cubes. Only 1 x squared, 0 x's, and 0 numbers. That lets us know a couple things. We know that a plus c has to equal 0. There's 0 x cubes here. There should be 0 x cubes on the right-hand side. We know that b plus d equals 1. We know that 2c minus 4a should equal 0. And we know that 2d minus 4b also equals 0. It's not an ideal world, but we can take these top 2 equations and substitute, which I'll do. That led to a whole lot of nothing. Turns out that a and c are both 0. Then we look at b and d. Doing a little substitution there, we find out that b is going to equal d minus 1. I substitute that in. D is 2, b is 1. That means this whole big, ugly equation up top can be written as, well, that's the answer, but there was a unique thing that happened there. I did my math wrong. I actually solved this for b and said d minus 1 when really it's 1 minus d. That threw off my numbers over here. So b and d are different. But I found that out by checking my work. Add those together to check